Welcome to a lesson with Dr. Powell. Let's take a look at how we can look at a group table and see if it's a group table or how we can build them. We have some kind of operation, just use a symbol for whatever operation it is. And we have some symbols. We'll need an identity, of course. Maybe we have some things here, some symbols here, and we want to create some kind of a group table. What are the criterion of what needs to happen? Okay, so we know that we need an identity. So using with the identity, so one, we're just going to call one the identity. So one times one, we'll just say times for whatever operation it is. So one times A, and we're just going to read like this guy first and then that guy from reading from left to right. So literally one times A is what we're going to be putting in right here, which is A. And so if we choose an identity, we can easily fill in those rows, A, B, C. And here, we're going to assume the identity works on the left and the right the same way, so that A times 1 is also A, and that's the same as 1 times A. So we're going to get A, B, C. So we need an identity in a group. What else do we need in a group? We need inverses. We need closure. We need associativity. Closure is pretty clear. We're just going to be using these symbols. So if we just use those symbols, we're good with closure. Inverses, well, in every column and every row, we need a 1 to appear exactly one time. We also need that the, so let's suppose, for instance, that A times B is equal to 1, all right? So if A times B is equal to 1, we're also going to assume that the inverses are two-way. They work both ways. So B times A is also 1. So we'll see some kind of symmetry in the 1s appearing. So in particular, if we thought of a symmetric matrix throwing out everything but just the 1s and making everything else zeros, it'll be a symmetric matrix, symmetric across this diagonal right here. So we think A times B would be 1, which means that this B times A is 1. At least in the ones that occur will be symmetric. Now, nothing else not necessarily needs to be symmetric, doesn't in general. However, in this case, well, maybe that's what it'll be in our case. However, in general, we don't need symmetry across this way, just with the 1s at least. So the 1s we need kind of some symmetry with, which in every row and column needs exactly 1, 1. So only one unique inverse. So C times C is 1. So C is its own inverse uniquely, and A and B are their unique inverses here. Okay, this is a small group, so actually we may just end up having symmetry overall. However, in general, that's not necessary. So inverses. Now, something else that happens with inverses, we can't repeat two things. For instance, what if we had a we can't have two things being the same. So it's kind of like saying like A times C is equal to B times C. What if these two entries were the same? Then, since C is an inverse, we could multiply by the inverse on this side, get the identity, and the identity times A would be equal to B, which we assume that these elements were different. So we can't have that. We can't have two things happening at the same time. So we have what we would call a Latin square, meaning that we can't repeat anything in a line. So that means every column is a permutation of the list, and every row is also a permutation of the list. So as long as we have permutations of the list in the columns and the rows, then we would be good with inverses, okay? So we'll remember that. Now, what about associativity? Okay, let's talk about what we need to do for associativity. Now, a couple things. One thing, realize that when we let's just take this row, and if we would multiply this row by, like, say, A, we should get this row. If we multiplied it by B, we'd get this row. If we multiplied it by C, we'd get this row. Now, if we take the row that's multiplied, where we multiplied everything by A, what if we further multiplied it by B? Then we would get the row that would be corresponding to BA, which in this case is 1, but in general, it could be something else. So we would get another row. And that row was obtained by first following this kind of arrow, like 1 goes to A goes to whatever that is, B goes to whatever that is, C goes to whatever that is. And then we get those things and we put them back onto this line, rearranged, and see where they go when we put in B. And in that arrangement, how that'll turn out is actually the row for BA, meaning that when we multiply right in here, like we multiply elements in this column together, really what's happening over here in the whole rows is we have a composition of permutations, meaning that that the group itself has the same structure as composition of permutations of where each row represents perhaps a permutation. That's Cayley's theorem. Okay, so really what in order to build this group, and that would actually give us associativity because we'd have permutations and composition is associative. So if we were just simply to pick our favorite subgroup of, see, there's 4 things here, favorite subgroup of S4, it's a collection of permutations with 4 things on it that has 4 elements in it. So a subgroup of size 4, a subgroup of this. Now this has permutations, say 4 times 3 times 2 times 1. That's the number of permutations that actually live in here. But if we take a subset of this that has size 4 itself, so there's lots of 4s, so keep them straight. This 4 only denotes that these are permutations of 4 things, but really that's how many permutations are in there. But if we take a subgroup of this collection, which has 4 things in it, and just structure our group table according to that with the permutations, we'd have everything we need here. So then we'd have associativity. So that would be nice. That's one way of doing this. Let's talk about yet another way, which is kind of cool. All right. So, and this particular method is adapted from a method. It's adapted from a method from Arnold Hamel, an article he wrote. And this is essentially how it goes. All right. So if we have somewhere in our group table, if we have a 1 appearing, and then maybe somewhere else where we have something else appearing and something else like this, then if we always have this coming up, AB happening right here, in this kind of setting, then we know it's associative for every rectangle that we find in our group table. So for instance here. So here, let's see, well, this is pretty clear because these are on the outsides. That's going to be B times B. But even like right here, what if we were to put something here? Suppose that we put A right here. If we put A right here, then let's see, suppose we put A, and that's okay because we have a B1, which would force this guy to be, but we can't put an A there because that would force that to be C, and that wouldn't work. So we're kind of forced here on things we can put in. But if we put in a C here, that's the only thing we can put in. And then here we can't, let's see, we can put a B in, we can't put a C and we can't put an A, but we can put a B in right here because I'm looking at this and this. So B, which would force this one to be C. But in general, you notice that, see, this B and C. So if we look at B times C, hey, that's exactly what goes here. Let's see, wait a minute, C times B. No, but this would be CB, right? Okay, CB, according to that rule. So let's see, so that means that whatever I put here has to go right here as well. So we kind of are restricted on what we put, and that's kind of, that associativity kind of gives that restriction there as well. So this would have to be an A, which would force that to be an A, which would force this to be a B for sure. Well, this is a very simple example here, but kind of the idea is whenever we see a 1 in a corner, we take what's vertical from it. So this rectangle could be in any place. Maybe it's like in this direction, or maybe it's in that direction or something. Like maybe you have something like this, like an A, one, whatever. You take what's vertical from it, and that's going to be what comes first. And then you're going to have an AB. So if you have a rectangle that looks something like this, you're always going to have this going on. You just take what's vertical from the 1. Okay, and that's going to be the first guy that comes right there if you have these two. Especially this is important for non-commutative type groups. And whenever you do that, whenever you see such a rectangle, if this always happens to be the result of multiplying A and B together, even if it's somewhere bizarre on the table, then we actually have associativity. In fact, if it's associative, this fact also holds. We can go over a quick illustration of that. So suppose for instance, that we have so we have something that looks like this, like a 1, an A, and a B. Okay, so and let's suppose that we know at least that the group is associative. So here, maybe the row has a K on this end, this column has an S, maybe this one column has a U, this has an R. So we know for sure that this is equal to RU, just from the group table itself. Okay, whatever that is. Now, we know that this is equal to KS, K times S is equal to 1, which actually means that S times K is also equal to 1. We'll use that fact because of inverses are double-sided. And we know this is KU. Okay, and we know that this guy right here is RS. All right, now let's take a look at RU for a minute. All right. Now, what if we were just to take RS and multiply by KU? Like this. Now, if we assume associativity, then we assume we can regroup like this. And now SK is equal to KS, which is 1, which means the whole thing is equal to RU. And what is RU? RU then is equal to RS times KU. And what is RS? RS is A and KU is B. Notice that assuming associativity gives us this happening, this nice idea that this actually works. Now, all right, now let's assume that this type of rectangle deal always works. Then if this kind of rectangle deal always works, then for instance, what if we had, okay, so let's just kind of give an example. Let's try to get A, B, C and show that that's going to be equal to that. All right. So let's kind of find some A in the table. Now in this table, there's going to be a 1. Maybe the one's above, maybe the one's below. Who knows? Okay. Now in this row right here, there's going to be a B occurring somewhere. It could be on this side or that side, wherever side. We're going to have the opposite side of that rectangle over here. And what's vertically placed from the 1, which is the A, will come first, which means this will be an AB. Okay. Now, next. Okay, somewhere in this column is going to be a 1. Maybe the one's here, 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 wherever it is. I'll just put it here for sake of simplicity. And then in this row, there's going to be a C occurring somewhere. Okay, now this guy, take what's vertical, so it's going to be A, B times C. That's what happens right here. Now, we also have, okay, now we also have something else happening here. We know that we know what this is, right? If we take what's vertical, this is like a rectangle right here with a 1 in this corner. Take what's vertical from the 1, it's B, so that comes first, BC. Now let's look at this rectangle right here. What's first comes an A and then BC, which means using that rule that this is the same as ABC. Hey, we've just proved general for any A and B and C, we have this occurring, associativity holds. So we can use that fact. So I just went through a brief little proof of that, of a group in a group table, associativity is equivalent to this always happening within these rectangles wherever we go. Okay, so that's something that can be used as we look at group tables. We build them. We consider whether or not they have they are associative as we look at them. So, for instance, let's try to look at this last example that we were just looking at. Notice, so 1, A, B, C, okay? Then this line is, yeah, it's 1, B, okay, so it's A and then C, okay. So looking at this line, see if this actually holds. I guess we already did, right? So, but let's just double check it. So here we have a 1, right? We have a B and a C. So this A better be BC. Is this, so BC, let's try it. BC is A. Okay, that's right. Okay, so that works. And if this is an acceptable group, then we'd actually have that occurring. So here we have, okay, so this would be CB, which we also had. Okay, yeah, CB, so that works. Look at another rectangle here. So let's do one right here. So this better be CA, or so CB, sorry, CB better be A, and let's try that. CB is A, very good. And we can walk through that. I wanted to kind of look at this and see if the permutation deal worked too. So this is the first. Okay, so this guy right here is a permutation where we take, okay, so it's like, in fact, we could think, for instance, so 1 goes to A goes to C. I'll just use cycle notation. A goes to C, and then C goes to B, and B goes back to 1. Okay, so we actually have a cycle, right? 4 cycle here. That's what that one represents. Now, what is this one right here? This one is like 1 goes to B, A, and then B goes to C, and C goes to A, and A goes back to 1. Okay, so we got that guy. Okay, and then this other one right here is kind of like 1 goes to C, C goes to 1. Okay, and then here we have A goes to B. So we have this. So it looks like, and then we have the identity. So it looks like we have 4 different permutations. And the question is, do these permutations themselves form a group? And if they do, that's another, because we have to check all these squares, right? I mean, yeah. I mean, it's a useful idea, but I mean, there's a lot of squares to check. Maybe it'd be simpler just to kind of look at the rows right here, get your permutations down, and then see, do these permutations really form a group? Or is it closed? Let's see. What happens if you run this one twice on itself? Then A would go to B back and forth because there's like 2 places to go, and then 1 would also be going to C. So if you did this one twice over on itself, you'd actually get this one. So that's good to know. All right. What happens if you did it 3 times over? So 1 would be going to B, and then 3 places over would be to C. Hey, that's pretty good. 3 places over would be to A. Yes. Okay, and then A would be going back to 1. So actually, which is the inverse of that. So, and then if you did 4 times, you get the identity. So it's actually like what you'd call a cyclic group, a rotation group, where you're just rotating it around like 4 vertices. So this is definitely a group. So the table that we just formed actually does work. This is a group table, albeit it's a very simple group. In fact, it's even a commutative group, cyclic and everything else, but yet a small example is nice when you're just kind of trying to play with these things. We also saw that we can look at little rectangles and discover when we look at those rectangles, this property, which kind of helps us to know if something is associative or not. All right, this concludes this little video. Thank you so much for watching.